The 2A3, sketching polynomials. I'm going to go over a few tidbits first. So I'm actually going to do this in two parts. One is going to be introductory. Some of you may actually not need this, and just move into some of the tidbits on sketching because this is not too complicated. So what we're going to do is we're going to sketch these polynomials, and a polynomial function in standard form comes in this right here, where we have ax to, say, a high power of 7, and then 6, and 5, and 4, and so on, with all these different leading coefficients that may do other things like stretch, compress, and so on. Now, just another tidbit, according to the fundamental theorem of algebra, all polynomials can be factored into their linear and quadratic components over the real numbers. Now, a lot of those quadratics can be irreducible, but that's basically what we're going to be looking at. We're going to start off with factored forms. Another tidbit of polynomials is that the polynomials a turn. They'll do funny things like this, all right? Or they can do very interesting things. And each one of these is going to be called a turn, where you have a local max or minimum. And you're going to have as many turns as n minus 1. I mean, it could be, at most, n minus 1 turns. So if we have a second degree polynomial, you'll have one turn. And you recognize that from a quadratic. You have one turn in the quadratic. A third degree, which is a basic cubic, can be like this. And that has one turn. Well, I drew that one with no turns. But it could be something like this. Okay, and there we have it. There we have two turns. So that would be 2, this would be 1. But it's at most. So as you see, I just drew a cubic with no local maximum or minimums. There's no turns. Fourth degree can have 3, and of course a fifth degree could have 4. Okay, and you can have fourth degrees that look something like this, like a little W, where you have 1, 2, 3 local max or minimums. Okay, moving on, and behavior is going to be a huge part of our sketching. And basically, there's a couple rules here. We're going to have rules for even, and we're going to have rules for odd degrees. So if we have like an x to the fourth, the leading coefficient is positive. So if I have 7x to the fourth minus 3x squared, whatever, okay? Oops, no, didn't mean to do that. Just basically something like that. The end behavior is going to be up. So, and again, if you remember your quadratic, where you have 2x squared or 3x squared or whatever, it's opening up. Okay? If the leading coefficient is negative, it's going to open down. And I actually used the quadratic for my even degrees just to keep me straight on the end behavior to the left. As x approaches negative infinity, it goes positive. As x approaches positive infinity, y goes positive. So that's what these mean right here. Okay? So again, I just revert back to your ax squared. Okay, if a is positive, it opens up. If a is negative, it opens down. For odd degree, I could think of my cubic. I can actually think of my linear if I wanted to. All right, ax or ax cubed. Doesn't matter which one I think of, because basically I'm starting at the low here and going up. So as x approaches infinity, y also goes to infinity. Okay, and as x approaches negative infinity, y will go to negative infinity. Okay, so actually I should have put that up here too. All right, there we go. And then the leading coefficient is negative. Think of the linear, your decreasing function right here. You're decreasing over the whole length. As x approaches infinity, y will go to negative infinity. And as x approaches negative infinity, y will go to infinity. They just flip. And I could think of the cubic, something x cubed, and I could think of the negative cubic of going down like this, like that, okay? That would be a negative cubic. Have these little examples memorized, and you're not going to mess this up. It's pretty straightforward. The degree of the polynomial is exactly what it means. It's the degree of the highest power. And you don't actually have to go and do all the distributive property and everything. All you're doing is just, this is to the first power. So you're going to have x third times x1 times x to the fifth. And that's just going to give you an eighth degree 3, 4, and 9. So it's going to be x to the 9. So it's going to be a ninth degree polynomial. Now to find the leading coefficient, you just multiply the leading coefficients. 2 times 1 times 2 times 2 times 2 times 2 times 2. Yay. All right. So that's going to be, and you're going to multiply it times 1 times 2, and you can find the leading coefficient that way. But that's actually not that important for our purposes. I know some teachers stress it, some don't. I'm kind of in the middle when it comes to sketching, because this is basically how much are you compressing or stretching or things like that on these leading coefficients. So 1, 2, 3, 4, 5, 2 to the 5th power is what, 1632 or something like that. Okay, so it's a really big number. Alrighty. What else are we going to look at before we get into some examples? That is it. I'll go ahead and post this video, and then we're going to get right into the examples. That way these videos are not too long.